So today's lesson is day 134, if we were still counting days in our notes. It's nuclear equations and transmutations. So a couple new things for us. Transmutation, if you think of mutation, like a genetic mutation, change in your DNA. A mutation is some sort of change from normal turtles to the teenage ninja turtles. So when one element changes into another because it gave off an emission of a proton or two from its nucleus, that's a transmutation. It's changing from one thing to the other. So the old fabled turning lead into gold. Can it happen? You bet it can. You can do a nuclear transmutation and make it happen, but it's so expensive it wouldn't be worth doing. And then nuclear equations is when a radioactive nucleus or atom wants to become stable. See, things don't want to be unstable. So they're going to give off particles to make their nucleus stable, whether it be neutrons or protons. And to get to that stability, they're giving off particles and they're turning into something, or at least we can see what particle they give off. We can do that through a nuclear equation, just like balancing equations again. Something fun. Woohoo! So get out your notes, your pen and your paper, pause when you need to. Here we go with our lesson. So what is a nuclear reaction? Well, a spontaneous nuclear reaction is the release of natural radioactivity to become more stable. So it just happens over time. Like when you were in earth science and you talked about carbon dating, that carbon-14 would just randomly, at a rate of 5,000 something or other years, we could check table N for that, and it's going to become stable. Now, a spontaneous nuclear reaction is one that is just a natural decay becoming stable. We also have what's called a natural transmutation. This is when, instead of just giving off a particle, now the element has given off a particle and has actually decayed into another element, like carbon-14 decaying into nitrogen-14. So an element of carbon that was unstable became an element of nitrogen, which is stable with those 14 for its mass. So it's a natural transmutation from one thing changing to another. So we can see here, we have radium. Now the top number is the mass number. The bottom number is the atomic number or number of protons. If Ra gives off an alpha particle is a 4,2 alpha or 4,2 He. So it has a mass of 4 and a charge of 2 or 2 protons because they have a positive charge. That means it's turning into Rn-222. So with these transmutations, we look at the arrow, the reaction arrow. And what we have to do is that's sort of like an equal sign. We can see down towards the bottom here is the equal sign. We need to take the top mass number and make the left side equal to the product side. So the reactant side equal to the product side. So 226 is the mass of the reactant. 4 plus 222 is the mass of the product. So 4 plus 202 is 226. They match, and they have to match. They have to balance. So we have to balance mass, and we have to balance the charge, the number of protons. So we have 88 on our reactant side. 2 plus 86 is 88. So we have 88 on the product side. So as long as everything balanced, we have a correct nuclear equation. So with different types of decay, we have alpha decay, beta decay, and others, but we can actually look at those particles and then figure out what one element will transmutate into. So in beta decay, there's too many neutrons in the nucleus, so it's too heavy. It's put it above the band of stability of the ratio of neutrons to protons. So what happens is that nucleus is going to give off that particle, and you can see the particle being emitted here. So that's a beta particle. So it's above the band of stability there. So in beta decay, we can see if we have too many neutrons, it's going to turn into a proton and an emission of a beta particle or an electron there, the 0, -1 e. So the neutron, a neutron has a mass of 1, but no charge. So mass of 1, same mass as a proton, but it is neutral, so no charge. Proton has a mass of 1 and a charge of 1. An electron has a mass of 0 and a charge of -1. So if we look at our reactant side, mass of 1, product side, 1 plus 0 is 1. So that is balanced. Reactant side has a mass of 0. I'm sorry, a charge of 0. Charge is on the bottom. And with a charge of 0, we have to have proton with a charge of 1 to make 0. We have to have a charge of -1. That's where we see this beta particle here coming into play. So in carbon-14, when it transmutates into nitrogen-14, it's beta decay. It has carbon-14 has 6 protons and 8 neutrons. Well, it's decaying into something with 7 protons and 7 neutrons because it's giving off this beta particle, this electron right there. So in beta decay, the atomic number is going to increase by 1. The number of protons is going to increase by 1. This is on the product side for each. The number of neutrons decreases by 1, and the atomic mass is going to remain the same. So when a nucleus emits a beta particle, which is a high-speed electron, when it emits a beta particle, these 4 things happen in the transmutation. Atomic number increasing by 1, so it's going to go up 1 on the periodic table. If the atomic number increases by 1, that's equal to the number of protons, so that's also increasing by 1, of course. The number of neutrons decreases by 1, and the atomic mass remains the same. So we have to have, for the atomic mass to remain the same, a decrease in the number of neutrons. So we can look at table N of the reference table, and when you look at decay mode, which is the 3rd column, you'll notice that the majority of elements that go through decay that we identify on our periodic table is beta decay. Beta decay is definitely the majority of what happens, giving off of a high-speed electron. Now we have what is called positron decay. If you look at table O, you notice that positron is just like a beta particle. It's that B, but it's got a positive sign with it. So for calcium-37, it does positron decay. It's a positive charged electron, which is pretty strange to think about. So in positron decay, there's too many protons. So those protons are going to convert to a neutron. They're actually below the band of stability. So their neutron to proton ratio is less than 1. So in this case, what we have here is magnesium transmutating into sodium. So instead of it increasing its atomic number by 1, we're decreasing the atomic number or decreasing the number of protons. So magnesium, its mass is 23 and its charge is 12, or it has a positive 12 charge because it has 12 protons in its nucleus. Having a mass of 23 means that it must also have 12 plus 11 is 23, so 11 neutrons. So when we go over to the product side, magnesium gives off this positron particle in positron decay. A positron has no mass and a charge of positive 1. So when we look at what magnesium transmutates into, 1 plus 11 gives us 12 for the charge. So we have to have something with a proton number of 11. 11 plus 1 is 12. 0 plus 23 gives us a mass of 23, which equals the reactant side, magnesium's mass of 23. So it would balance out. So in positron decay, the atomic number is going to decrease by 1. The number of protons decreases by 1 because number of protons is the atomic number. The number of neutrons increases by 1, and the atomic mass remains the same. So these are those facts that what we look at as we do this. Alpha decay. Alpha decay is when the nucleus is too heavy. It's basically got a mass of 4 now because that's the mass of a helium. Alpha decay is a transmutation because the atom changes its atomic number and becomes a different element. So in alpha decay, we're giving off something that has a mass of 4 and a charge of 2. So 2 protons, 2 neutrons are being released with this particle, and that would be considered an alpha particle. As we can see this one here, as this nucleus wants to become stable, it emits that particle. Alpha decay, typical radioactive decay of uranium. Here we can see uranium 23892. It's going to decay into thallium. So we've got 238. If something with a mass of 238 gives off an alpha particle with a mass of 4, 238 minus 4 is 234. So the new element it transmutates into, TH, has to have a mass of 234. If uranium has an atomic number of 92 or 92 protons, if it gives off 2 protons, that means that we have a decrease in atomic number or a decrease in the number of protons by 2 in the element is transmutated into. So the atomic number is 90. So what we actually do is we mathematically figure out these numbers, and then we look at our periodic table to see what element is turning into. So in alpha decay, their atomic number decreases by 2. The number of protons decreases by 2 because the number of protons is the atomic number. Number of neutrons decreases by 2, and the atomic mass is going to shrink and decrease by 4. So those are types of decay, but we've demonstrated them with what is called a nuclear equation. In a nuclear equation, charge and mass must balance. So what you find on top must balance from left side to right side, reactant side to product side. What you find on the bottom, the charge, that must be equal from reactant side to product side. So what's equal on left equal to on right. So it's basically two math equations where you're splitting them at the reaction arrow. There's your equal sign. And then the top must equal the top, the bottom must equal the bottom. So the top is the mass, the bottom is the charge or number of protons. It may be annoying, but you're going to come to love it. So what I'd like you to do is pause the video. You'll have these 3 choices right here, 3 reactions to do. What I like to do is try and figure out what is the missing reactant or product. So hit pause. When you've got your answers, hit play, and let's see if you are right. All right, you've got your answers. Welcome back. So on top, 242 equals 4. If it gives off a helium particle, alpha particle, 4 plus what is 242? You should have had 238 on top. All right, we have 94 for our charge. If it gives off a helium particle and alpha particle, 94 equals 2 plus what gives me 94. So 2 plus, it should be 92, gives you 94. Then you look up element number 92 in your periodic table. What is element number 92 in the periodic table? You've got uranium. So it's uranium-238, 92. In the next problem that you just did, we have sulfur 3216. And it is giving off, in this case, looks like beta decay. This is an electron, 0, -1e. So what is 32 plus 0? 32 plus 0 is 32. So that should be the mass of our reactant. What is 16 minus 1? 16 minus 1 is 15 for its number of protons. So there's its atomic number. You look that up in the periodic table, and that gives you phosphorus. So it's P3215. What kind of decay is that? That is beta decay. You beta remember that one. The bottom one, you have oxygen 15-8. Uh-oh, that little thing goes in the way. With oxygen 15-8, we have what plus 0 gives me 15. That's going to be 15. On the bottom, 7 plus 1 gives me 8. If I move the mouse over there, that bottom chart keeps coming. So 7 plus 1 gives us the number of protons. And when you look up atomic number 7 on the periodic table, you should have found that it was nitrogen. So it's nitrogen 15-7 is what oxygen 15-8 has transmutated into during what kind of decay? So you look at table O, 0, positive 1e is positron decay. So that's exactly how you do nuclear equations. I sort of find them fun. It's like a puzzle. So they did experiments, and this is back to Ernest J. Rutherford. You remember him from the gold foil experiment, shooting alpha particles through the thin leaf gold foil, and most of the particles went straight through, and with that, they proved that the atom is mainly empty space with a tiny, dense nucleus. Ernest Rutherford and his team also did experiments to separate the different types of radiation. So they took different elements, different radioactive material, and they put positively charged surfaces on one side, we see here on the right in this diagram, negatively charged surfaces on the left, and then they had some sort of photographic paper or plate in the back. So when the particles, radioactive particles, were emitted from whatever they put in their block, they could see on the photographic material that if it was pulled towards the positive side, what's attracted to positive? Negative. So what are negative? Negative are beta particles. If the particles ended up on the photographic plate on the left, bending towards the left, that means they were attracted to the negatively charged block. What's attracted to the negative? That would be positive. So what kind of particles are positive? Could have been positrons, could be alpha particles. And they found that if particles were emitted and they went straight through, they were not deflected by the positive or negatively charged blocks. They just went straight to the photographic plate. They knew that those were gamma radiation, because gamma radiation has no charge, also has no mass, but because it has no charge, it's neither attracted to positive nor negative. So these guys, Ernest J. Rutherford and his team, and lots of other scientists at the time, figured out that if things naturally transmutated, well, what would happen if we bombarded elements with particles? That you could actually make nuclei unstable and you could force them to transmutate into something else, sort of like the Hulk getting Bruce Banner getting angry and turning into the Hulk. So they figured out how to do what's called artificial transmutation. And that's when you can artificially force one element to change into another one by bombarding it with a particle. So if I have something and I want it to be 2 elements higher on the periodic table, I know that I have to bombard it with an alpha particle, giving it 2 extra protons. So you could change things. You can decrease on the periodic table the atomic number or increase. So in artificial transmutation, when we look at our equations, there's going to be 2 particles on the left. There's going to be the element, and then whatever particle you're bombarding it with, and then the products will be whatever it's turning into, artificially transmutating into, and sometimes whatever else it's giving off with it. So this is a good old picture of Ernest J. Rutherford here. It was quite the soup strainer mustache they gave him. But he was the first one to do this. He took nitrogen-14, bombarded it with alpha particles, and turned it into oxygen. In this case, taking an element that really wasn't radioactive, a stable element, making it unstable, and converting it into an element that was needed. So he did this, and actually he was able to prove the existence of protons this way, which was a huge step for chemistry. So artificial transmutation. And this is where you bombard something with a particle. So you're going to have that bombarding particle on the reactant side. So natural transmutation is just one thing as a reactant and naturally turns into something else. Artificial transmutation, you have the one thing and then whatever it is you're artificially hitting it with. Sort of like when you artificially make your brother extra mad and flip out so you can get in trouble in front of his parents, your parents. So you have a target and we have a bombarding particle. All right, well, that's it for today's lesson. Go back over it if you need to. There's a lot there. We'll do some practice in the learning check. And the video that's attached is going to go over the nuclear equations. So in the next slide, look at that video. It's only 3 minutes, 38 seconds. And it will go over the nuclear equations a little bit more for some more practice for yourselves.